Okay, this video is for the AQA Required Practical 3, Factors that Affect Resistance. It's going to be focusing on how the length of a wire affects its total resistance. Okay, so you'll need to have some idea of a method and a diagram. Now, because it's a electricity practical, you're going to have to draw the circuit diagram. It's going to look at something like this. You want a simple method. Think about what's a really good start for methods. In nearly every science practical that I can think of, a really good opening line is set up as shown in the diagram. In this case, it would be set up as shown in the circuit diagram. It's a really good place to start your method. Now, this is about Ohm's law. So we're looking at how voltage and current can be used to calculate the resistance of the wire. Okay, and that's what Ohm's law tells us. That equation that links those three things together: the potential difference, the current, and the resistance. Okay, and then with those, we want to think about, okay, so we're going to be varying the length of the wire, and we're going to be looking at its resistance. What kind of graph do we get out? Okay, are the results directly proportional? Are they not directly proportional? Okay, we want to think about those results. It's an electricity practical, and we need to think about how we stay safe. So what are the hazards? How do we control them? How do we make it safe to do the practical? And this example, the biggest error and the hazards are actually linked quite closely. Okay, what might be the biggest source of error? So let's think about that as we go through. So the first thing we're going to look at is the method and the diagram. So here is my simple series circuit. This is the test circuit we're going to be using. So we've got a battery providing our potential difference. Okay, you could use a cell, you could use a power supply. We've got an ammeter that we're going to be connecting in series with our test wire. Okay, the ammeter is measuring the current. Okay, and we've got these crocodile clips that allow us to adjust the length of the wire that we're looking at, so we can control that length. And then we go back round, we go into a switch and back into our power supply or battery. Then across the crocodile clips, so we can measure the potential difference, we've got a voltmeter. Okay, so this allows us to look at the potential difference across the piece of wire and the current at the same time. And then we can use those two things to calculate the resistance. So here's a really brief method just to set up as shown in the circuit diagram. Record the length accurately using a meter ruler, so using the scale of the ruler. Measure and observe the potential difference with a voltmeter and a current with the ammeter, and then we can use those to calculate that resistance. Okay, now if you want to improve this method, think about some ranges. What will be the length that you could start with? Okay, are we doing 1 millimeter, 2 millimeter, 3 millimeters? So we're doing 1 meter, 10 meters, 100 meters. Think about a sensible range that you're going to investigate over that piece of wire. Okay, in my experiment, I went from 30 centimeters to 100 centimeters in 10 centimeter steps. Okay, it's a sensible range. Okay, some theory. So this practical is looking at how that voltage, current, and resistance are linked. How the potential difference, okay, and the current are linked to that resistance. So we're using those two measurements to calculate that resistance. Okay, because we want to see what happens to that resistance if we make the wire longer. Is the resistance going to go up? Is it going to go down? Is it not going to have an effect at all? Okay, so we want to think about what's going to happen if we make the wire longer. Now this is a simple cartoon of what might be happening inside the wire. So we've got these positive circles, okay, positive circles which are metal ions, and we've got these little blue dots which are the delocalized or free electrons. These are the electrons that can travel through the wire and pass on that electricity. Okay, that's what the current is, these flowing electrons. Now when they bump into and collide with these metal ions, that's where resistance comes from. So what's going to happen if I make this piece of wire longer? Will there be more collisions or less collisions? Is it going to be harder for the electrons to travel all the way through or easier? So I want you to think about that while you think about what's going to happen if we make that wire longer. What's going to happen to the resistance? Okay, it's a good point to maybe jot down a prediction. Okay, so here is the experiment. Now it's hard to see the wire, but there is a wire connected between these two crocodile clips. And the setup is pretty simple. So we've got a power supply instead of a battery. We come from one terminal through the wire into our ammeter. This is our ammeter. Okay, and then that flows through the second wire into our crocodile clip, into our resistance wire that travels along the meter ruler, into a second crocodile clip, round we go, back into our power supply. Now we've got a voltmeter and an ammeter to record the voltage and the current. We've got it set to DC. We want a constant amount of potential difference, a constant voltage across this wire. Okay. Once we turn on our power supply, we'll set this to a sensible voltage. So depending on the resistance wire, we'd like this to be relatively low current, so certainly below an amp, so they go a little bit high. But once we've set it up, we can see these values and we can record the current flowing through the wire and the voltage across that wire, and we can calculate the resistance. Okay, so we calculate the resistance for those two numbers. We then switch it off before we move the wire, because this wire gets hot. Okay. We can then safely, once it's cooled down a little bit, we can do microcolor clip, move it to the next measurement. So this was 50, and then we're going to 40 centimeters or 30 centimeters, whatever result it would be, and we can get a new set of values. Okay, and then we just repeat this setup across the range that we have chosen. So I went from 30 centimeters all the way to a meter in 10 centimeter steps. Now I'm not going to show you that because it would be a bit dull. Okay, so here is my results table. So we've got length on the first column, starting at 100 and went all the way down to 30 in 10 centimeter steps. Then we've got the potential difference, starting at 1.2 volts, dropping down to 0.75, and we've got the current. So here is a good point to practice how to calculate that resistance. How would we do it? So you could pause the video here and you can try and calculate that resistance value. So my next slide, if you haven't done that and you want to, is where I've calculated that resistance. So this is the set of results. Now I've got the length decreasing, so we've gone from 100 to 30. Okay, my length is going down, my resistance is going down. Or my length is going up, and my resistance is going up. But just having it in a table isn't good enough. To really understand what's happening with the results, we need to put it into a graph. And we're going to plot along the bottom of my axis the length in centimeters, and the resistance in ohms. Okay, and this is the plot we get. Okay, so we've got length along the bottom from 0 to 100, and we've got resistance from 0 to 8. Okay, and we can add a trend line to this, line of best fit. Okay, and that goes through 0 and goes through all of my points. You need to be able to describe what type of graph this is. Okay. So you can pause the video here and you can tell your teacher, you can tell somebody else what type of graph this is, because it's important that you're able to describe it. So this is a directly proportional relationship. The length is directly proportional to resistance. It's a straight line that goes through 0. So as the length increases, the resistance increases, which is to be expected. As I increase the length, the number of those collisions between the electrons and the metal ions goes up. The longer the wire, the higher the resistance. Okay, now onto our safety, onto our hazards. Now I've changed the setup a little bit. I've shortened the length down past 10 centimeters, it's only 5 centimeters. I'm increasing the potential difference a little bit, and when I turn it on, my piece of wire gets hot enough that it sets the ruler on fire and almost sets on fire my splint. Okay, that's the first thing you might notice. The second thing you might notice is the current here. It spikes at 8.5 and then goes off the scale and then goes to 0. So the current was high enough that I couldn't read it with this ammeter. I'd have to have a better ammeter to actually find that real current. And it got so hot that the wire melted and broke the circuit. So this is why this experiment is actually dangerous. It's not the electricity itself. Okay, the chance of getting electrocuted is quite slim. Okay, it's getting burnt that is the big hazard. Okay, so you think about how can we mitigate that? How can we reduce the chance of getting burnt? Okay, and that's why it's linked to our error. Because if we heat up the wire, or if we cool it down, the resistance of that wire will change. Think about why. So when the wire gets hot and the resistance goes up, that's going to affect our results. That will add error to our results. So to improve this experiment, to improve our method, we could change it so we maintain a constant current. We can alter the applied potential difference. We can change that potential difference to keep the current constant. And that will mean that the wire temperature should be constant, okay, especially if you have a low current. And that will reduce that big error. And then our hazards, heating of the resistance wire is our biggest hazard. the consequence, what could happen because of that hazard, is burns to the skin. And then to control it, we don't touch the wire while the circuit's on. We allow the wire time to cool. And another good technique would be to have a relatively long minimum distance. So don't decrease the length of that resistance wire past 10 centimeters or 20 centimeters. Okay, so here are our 4 boxes that we need to complete for our required practical. We need some information about the method and diagram. Okay, this is just hints and tips to how to get started. So I've got setup as shown in diagram. Maybe you could add circuit diagram to that. A little bit about the theory. So what is the equation we're using? Maybe you can write down the rearrangement. You can give an example of a calculation. You can talk about a diagram showing where that resistance comes from. So we've got our metal ions and the electrons here. We've got results and conclusions where we can plot a sketch graph showing that length against resistance, talking about whether it's directly proportional or not. It is. And then in our hazards and errors, we're talking about if the wire heats up and the resistance changes, how can we stop that from happening? And how do we stop getting burnt? Okay. The only thing you want to include is what are our independent variable, our dependent variable, and our control variables. Okay, we want to add those to our results and conclusions. Okay, so best of luck in putting your little works bits together. Okay, and another one of these will be coming soon. Take care and bye-bye.